You're not going to believe how far ahead China is when it comes to building the future. While America's still patching potholes and arguing over budgets, China is blasting through mountains, raising megastructures in days, and unveiling tech so advanced it makes US infrastructure look like it's stuck in the Stone Age. From bridges that make the George Washington Bridge look like a toy, to cities that rise overnight, China isn't just catching up. They've lapped the US, and they're not slowing down. So how did this happen? What secret tech is powering China's rise as the king of megaprojects? In today's video, we're diving deep into China's mind-blowing engineering power, exposing the game-changing construction tech that has even world leaders stunned. Don't forget to subscribe and turn on notifications. We've got a lot to uncover, and trust me, you won't want to miss what's coming next. China's engineering marvels. As one of the world's largest developing nations, China has consistently fueled its economic and social growth through a relentless focus on infrastructure. Chinese engineers have emerged as the driving force behind this development, standing as titans in the field of construction. They have devoted their efforts to creating monumental projects that meet the evolving needs of a population that continues to expand. From the Baihetan hydro power station that rises along the banks of the Jinsha River to the cloud-kissing spirals of the Yaxi Expressway tunnel, these projects demonstrate a remarkable commitment to pushing the boundaries of what is possible. Throughout China, engineering feats have redefined the limits of human capability. The Qinghai-Tibet Railway, which sits at the highest altitude of any railway in the world, and the Hong Kong-Zhuhai-Macau Bridge, which spans the Lingding-Yang, are only two examples in a long list of achievements. Engineers have tackled the near impossible by conquering the hellish terrain of the Sichuan-Tibet Railway and by carving a 50-meter deep tunnel beneath the Pearl River estuary. These challenges did not deter them. Instead, they provided opportunities to showcase innovation on an unprecedented scale. While debates in other countries continued over how to repair aging bridges, China moved forward at a breakneck pace, reshaping its landscape by constructing 16,000 kilometers of highways and 4,000 kilometers of high-speed rail each year. In 1949, China's railway network measured only 21,000 kilometers, with nearly half of it in disrepair. Few could have imagined that, within just 75 years, the country would build a transportation network comprising 45,000 kilometers of high-speed rail and 180,000 bridges. This network now allows people to travel thousands of miles in a single day, linking cities and regions with remarkable efficiency. Behind this achievement lies a deep-rooted Eastern philosophy that challenges conventional Western perceptions. During the construction of the Husutong-Yangtze River Bridge, Chinese engineers developed a specialized steel with a tensile strength of 500 MPa. This steel is strong enough that a cable the thickness of a chopstick could theoretically lift 3 main battle tanks. This breakthrough in material science made it possible to design and build a cable-stayed bridge for both road and rail with a main span of 1,092 meters, a structure that once existed only in theoretical concepts. The Husutong-Yangtze River Bridge, now the world's first road-rail cable-stayed bridge with a main span exceeding 1,000 meters, not only connects key regions along the Yangtze River economic belt, but also serves as a symbol of China's leadership in infrastructure innovation. Its design includes 2 towering 330-meter-high diamond-shaped main towers, each equivalent in height to a 110-story building. These towers endure axial forces of 300,000 tons, stabilizing the bridge like the mythical sea-calming needle, their massive foundations embedded deep into the riverbed, mastering materials and terrain. To overcome the complex hydrological conditions of the lower Yangtze River, engineers pioneered a cutting-edge precision positioning system for maneuvering a 15,000-ton steel caisson. They constructed a massive foundation spanning 5,100 square meters on a sediment-laden riverbed, an area equivalent to 12 basketball courts. This accomplishment set a new world record and demonstrated how Chinese engineers could not only adapt to difficult environments, but master them. The bridge relies on ultra-high-strength steel developed in China, which surpasses conventional materials in durability and resilience. Combined with 2,000 MPa-grade stay cables, the steel and concrete structure supports a staggering load of 480,000 tons of steel and 2.3 million cubic meters of concrete. This quantity of steel equals what was used to build 12 Bird's Nest stadiums, while the concrete matches the volume found in 8 national grand theaters. The Husutong Yangtze River Bridge transformed regional transportation. It reduced the travel time between Nantong and Shanghai from 5 hours to just 1, revitalizing the transport network in the Yangtze River Delta. Much like meridians in traditional Chinese medicine that unblock vital energy flow, this bridge has unblocked critical transportation arteries in the region. It now carries multiple transport lines, including the Tongxi Expressway, Huzhou Railway, and Tansu-Jiayong High-Speed Rail. The bridge handles more than 100,000 vehicles daily and supports 80 million tons of freight annually, serving as a vital corridor linking China's coastal economic zones. Its 1,092-meter-wide main channel accommodates vessels up to 100,000 tons, ensuring seamless integration of maritime and land-based transport. International observers have been captivated by the spectacle of the bridge's steel beam closure process, a feat broadcast and shared widely across global media platforms. Through such projects, China's engineering standards are gaining international recognition. While some countries continue to debate infrastructure plans, China defines the future by executing them. The world has taken notice, not just of the projects themselves, but of the speed, scale, and precision with which Chinese engineers are delivering them. Beneath the waves of the Lingding Channel, a different kind of engineering marvel unfolds: the Hong Kong-Zhuhai-Macau Bridge's undersea tunnel. This 6.7-kilometer steel structure quietly connects 3 major cities, marking a new pinnacle in China's infrastructural achievements. As the world's longest road-immersed tunnel, it symbolizes not only technical mastery, but also the willingness to take on immense challenges. Chinese engineers chose an underwater route not for spectacle, but to overcome dual obstacles: heavy maritime traffic and environmental constraints. Above the surface, ship navigation required clear and unobstructed passageways. Below, the sediment-rich seabed and shifting currents presented their own hazards. Engineers responded with boldness and precision, constructing an immersed tunnel that could withstand both the weight of the sea and the pressure of intense usage. But why did Chinese engineers choose this underwater path? The Lingding Channel Tunnel. The waters of the Lingding Channel are among the busiest in the world, hosting dense networks of international shipping lanes and vital flight paths beneath Hong Kong International Airport. Constructing traditional bridge towers across this critical zone would have posed serious risks to maritime traffic and aircraft operations. Furthermore, the seabed, characterized by dynamic sedimentation, made conventional piers unstable and unfeasible. Faced with this intricate challenge, Chinese engineers demonstrated unparalleled vision and innovation. They designed and executed a groundbreaking bridge island tunnel cluster that redefined what deep-sea infrastructure could achieve. To navigate these complexities, the team devised artificial islands to serve as seamless transition points between the surface bridges and submerged tunnels. This ingenious design safeguarded navigation routes, eliminated airspace obstructions, and conquered the geological instability of the seabed in one comprehensive solution. At Zhuhai's Nyoto Island, engineers constructed the world's largest immersed tube prefabrication facility, a hub where 33 massive tube sections came to life. Each of these tubes stretched 180 meters long and weighed an astonishing 74,000 tons, roughly the size of a medium aircraft carrier. Producing components of such magnitude required not only scale, but also precision. Pioneering the curved immersed tube factory method, engineers fabricated tube sections with a curvature radius of 5,500 meters, achieving millimeter-level accuracy. This technique broke the limitations of traditional straight-line production and marked a leap forward in tunnel prefabrication technology. Once completed, these colossal tubes had to be transported from the prefabrication yard to the construction site, a journey that required careful planning. Engineers relied on a formation of 8 high-powered tugboats, all coordinated through satellite positioning and an intelligent control system. With this advanced navigation technology, they positioned each section with exacting precision in the open sea. Harnessing the natural buoyancy of water, the engineering team then guided each immersed tube section to descend gently to its designated trench on the seabed, 44 meters below the surface. Using China's independently developed deepwater unmanned installation system, they achieved extraordinary connection accuracy, aligning each section with a joint tolerance of only 3 millimeters. International media outlets hailed this level of precision as the subsea kiss of perfection, a feat of engineering that combined meticulous planning, advanced materials, and technological prowess. Traditional immersed tunnel construction relies on underwater welding, a laborious and risky method to ensure watertight seals between sections. Chinese engineers abandoned this outdated technique in favor of a revolutionary solution: active compression sealing technology. They installed retractable steel bulkheads at the ends of each tube and employed hydraulic systems to compress rubber gaskets actively. This transformation from manual labor to mechanized operations ensured complete water impermeability and allowed the final joint installation to be completed within a single day. This innovation boosted construction efficiency by tenfold, setting a new benchmark in tunnel engineering. Throughout the entire installation process, engineers used high-precision micro-electromechanical gyroscopes and tilt sensors to monitor the immersed tube's positioning. These tools captured ultra-low-frequency motion data in real time, enabling the team to adjust and verify the alignment of each tube section as if assembling perfectly interlocking building blocks. This meticulous approach guaranteed the structural integrity of the entire tunnel and allowed for seamless continuity across all 33 sections. At both ends of the tunnel, engineers constructed artificial islands reinforced by steel cylinder retaining structures. They drove 120 steel tubes, each measuring 22 meters in diameter, deep into the seabed to create a foundation capable of withstanding powerful ocean currents and the frequent typhoons that batter the region. These structural elements provided the necessary stability and resilience to support the immense loads and stresses imposed by the environment and the infrastructure itself. Before the Hong Kong-Zhuhai-Macau Tunnel, no immersed tunnel in the world had ever extended beyond 3.5 kilometers. From the Orson Strait in Denmark to Busan in South Korea, projects of this nature faced limitations in length, complexity, and feasibility. Chinese engineers shattered that barrier with a record-breaking 6.7-kilometer undersea span. They executed this monumental feat by aligning 33 colossal tube sections on the seabed with a cumulative error smaller than the width of a human hair, a level of precision that stunned international observers and redefined global standards in deep-sea infrastructure. Setting global benchmarks in tunnel construction. Through the Lingding Channel Tunnel, Chinese engineers demonstrated how visionary design, technological innovation, and flawless execution could conquer natural obstacles and create new opportunities for connectivity. The tunnel's existence is not only a marvel of engineering, but also a testament to China's commitment to redefining infrastructure on a grand scale. This project addressed dual challenges that once seemed insurmountable: maintaining safe passage for maritime and air traffic while building a structurally sound tunnel on an unstable seabed. By constructing artificial islands, engineering curved tube segments, and leveraging unmanned systems for deep water installation, the team introduced a new paradigm in tunnel construction. Their use of active compression sealing technology eliminated the risks associated with traditional underwater welding and drastically increased efficiency. Meanwhile, real-time data collection and precision positioning ensured flawless integration of each tube section, delivering a final structure that not only functioned but excelled beyond previous limits. International media, governments, and engineering communities around the world acknowledged the tunnel as a revolutionary project. By overcoming engineering limitations and completing the world's longest road-immersed tunnel, China has solidified its status as a global leader in deep-sea infrastructure. The Lingding Channel Tunnel stands not just as a link between Hong Kong, Zhuhai, and Macau, but as a symbol of what human ingenuity can achieve when vision and execution align. Pushing the boundaries of subsea engineering. The Lingding Channel's 6.7-kilometer undersea tunnel has done more than connect cities. It has elevated China's status from a follower of infrastructure standards to a global leader in engineering innovation. This remarkable passage under the sea demonstrates that China's technical prowess can tame even the most challenging marine environments. Through this project, Chinese engineers have not only built a transportation lifeline, but also inscribed a bold new chapter in the history of human engineering. Yet, the Lingding Tunnel is not the only feat that has left the world in awe. Another colossal project, the Shenzhen-Zhongshan Link, has stunned international observers and further cemented China's place at the forefront of megastructure development. Stretching an astonishing 24 kilometers, the Shenzhen-Zhongshan Link stands as an integrated cross-sea engineering marvel. The project combines bridges, islands, tunnels, and underwater interchanges into a unified whole, including a 6.8-kilometer undersea tunnel. More than a connection between two cities, this link serves as a core transportation artery for the Guangdong, Hong Kong, Macau, Greater Bay Area, a region driving much of China's economic momentum. What makes this tunnel unique is not just its length, but its technological sophistication. Engineers embedded 23,000 fiber optic sensors inside the immersed tubes, giving the concrete the ability to sense stress changes in real time, much like a nervous system in the human body. This innovation makes the sensors 40% more sensitive than comparable Western technologies. The journal Nature remarked on this advancement with astonishment, noting that China has, in effect, taught concrete how to think. Engineering against the odds. To understand the scale of the Shenzhen-Zhongshan Link's tunnel, consider its design: a dual-direction, 8-lane configuration with 2 more lanes than the Hong Kong-Zhuhai-Macau tunnel. The tunnel comprises 32 enormous immersed tubes and 1 final joint, all buried over 40 meters beneath the seabed. When Dutch experts declared an 8-lane immersed tunnel impossible, Chinese engineers responded by staging a subsea engineering marvel in the treacherous waters of the Pearl River estuary. They introduced an innovative steel-concrete sandwich composite structure, breaking free from traditional Western engineering conventions and setting a new global standard. Traditional immersed tunnels typically rely on cast-in-place reinforced concrete, a laborious, time-consuming process that poses significant logistical challenges. Chinese engineers chose a different path for this project, adopting a steel shell design that allowed for greater efficiency and structural strength. The 8-lane configuration, however, widened the tunnel significantly, with each additional lane increasing hydrostatic pressure by 27%, equaling approximately 20,000 metric tons per lane. This means the structure had to bear the equivalent weight of 15,000 sedans per lane. On top of that, the tunnel had to support a navigation channel overhead that accommodates 10,000-ton cargo vessels. The engineers faced dual pressures. From the sea and from above, creating a scenario akin to the crushing forces experienced by a beverage can underfoot. The risk of deformation was real and demanded a novel solution. After extensive research and testing, the engineering team opted for a steel shell concrete structure. They began by fabricating the steel shell of each tube, then filled the interior with concrete, a hybrid construction method that greatly enhanced compressive strength and eliminated the need for traditional rebar tying. This composite structure increased flexural rigidity by 400%, a breakthrough so significant that the American Society of Civil Engineers has since included it in their latest design standards. To ensure precision and durability, engineers relied on cutting-edge automation throughout the production process. Inside an advanced automated facility, steel plates were cut into precise profiles and assembled using robotic welding arms. These intelligent arms achieved a seam alignment accuracy of 0.2 millimeters, one-third the width of a human hair. Certification tests conducted by Germany's TÜV Rheinland confirmed that the weld quality exceeded DIN 6700 standards by 22%. Due to the massive scale of each tube, engineers divided them into 22 segments. Once individual segments were completed, gantry cranes assembled them, and the final assembly was completed by a skilled crew. But beyond structural integrity, ensuring long-term corrosion resistance posed another critical challenge. To protect the tunnel for a century of underwater service, engineers applied 5 layers of anti-corrosion coating to the steel shell. This coating mimicked the molecular structure of shark skin, leaving no surface for algae or bacteria to cling to. Each tube section was then equipped with 552 sacrificial anodes, devices designed to corrode in place of the steel shell, ensuring the entire tunnel would remain free of corrosion for at least 100 years. Once the steel shell was completed and protected, engineers transported each tube to a separate facility for concrete infill. The tunnel's steel shell concrete structure required more than 1 million cubic meters of concrete to fill all 32 tube sections. Manual labor alone could not handle such volume efficiently, so engineers turned to intelligent concrete pouring robots. These robots followed pre-programmed routes along the top slab of each tube, autonomously detecting drilling points and performing the pouring operation with no human assistance. Using 1,200 embedded sensors, the robots continuously monitored and adjusted the concrete flow rate, compressing a process that once took 90 days into just 28 days. One of the most astonishing features of this process was the zero manual vibration technique. Engineers used self-compacting concrete that flowed into every crevice with precision comparable to the distribution of capillaries in the human body. It moved like melted dark chocolate, achieving millimeter-level accuracy. To perfect this process, the engineering team dedicated 3 years to research, developing the ideal composition ratio and building a full-scale tube module for testing. This simulated the tunnel's ability to withstand over 1,000 typhoons, a level 9 earthquake, and a projected sea level rise of 3 meters by the year 2075. This philosophy of embracing risk in order to achieve innovation, a die-before-rebirth approach deeply rooted in Eastern thinking, reduced overall project risk by 83%. Through their bold vision and technological mastery, Chinese engineers not only built the world's widest immersed tunnel, but also redefined the boundaries of what is possible in subsea infrastructure. The final steps in building the Shenzhen-Zhongshan undersea tunnel. The specialized concrete used in the immersed tubes of the Shenzhen-Zhongshan link underwent rigorous simulation tests, which confirmed its reliability and effectiveness for use in this massive infrastructure project. Engineers ensured that this concrete not only met strength and flowability requirements, but also maintained consistency throughout the casting process. However, they faced a critical challenge. The concrete had to be poured within 90 minutes of leaving the batching plant. This tight timeframe drove the creation of an intelligent manufacturing facility designed specifically to streamline and accelerate the casting process. The facility could produce one complete tube section each month, earning the moniker Smart Dream Factory for immersed tube prefabrication. Each complete steel shell immersed tube weighed an incredible 80,000 tons. Transporting such a structure even 200 meters to the departure area posed a formidable challenge. Engineers overcame this by deploying a coordinated system of 200 transport vehicles operating over more than 1,000 steel wheels. Through this logistical marvel, they moved each tube to the departure area in just 4 hours, a process that previously took 7 days for structures of similar size. Before a tube could move in or out of the facility, workers conducted meticulous final inspections using non-destructive testing equipment with millimeter-level precision. These tools allowed teams to assess the density of the concrete without damaging the steel shell. Once a tube passed inspection, workers fitted it with ballast water tanks and steel sealing doors, then guided it into a deep water dock using carefully calculated buoyancy controls. With the tube ready for installation, the next phase involved preparing the seabed for the tunnel's placement. Excavating a 5-kilometer-long, 330-meter-wide trench 40 meters beneath the ocean surface required not only precision but also specialized machinery. The seabed in the undersea tunnel section contained uneven, weathered rock, making it unsuitable for direct placement of the tubes. Engineers needed to level this terrain first, and they brought in powerful drilling tools to do the job. A 35-ton drilling hammer, weighing as much as 3 main battle tanks, descended in freefall to crush the granite below. Each impact delivered energy equivalent to 2.5 kilograms of TNT. Despite this force, the hammer operated with incredible precision, maintaining trench depth within a tolerance of plus or minus 4 centimeters, a level of accuracy more exacting than the standards used to install park benches in New York's Central Park. While the drilling hammer pulverized the rock, another vessel equipped with a powerful grab bucket cleared away the resulting debris. Engineers likened this process to laying a bed for the immersed tubes, with the subsequent stone-laying phase acting like adding a mattress to ensure perfect alignment. The leveling vessel Jinping No. 2 took center stage in this critical task. Upon arriving at the precise tunnel location, the vessel deployed 4 70-meter-high support pillars, anchoring itself firmly into the seabed. Conveyor belts carried rubble to the stone-laying pipe, which discharged the material evenly at a controlled speed. This process achieved a consistent stone bed, with deviations no greater than 4 centimeters. Crews completed the leveling work for each tube section every 4 days, steadily preparing the trench for final installation. Once the trench was ready, the world's first integrated floating and installation vessel, Jinan No. 1, began the next stage. Loaded with an 80,000-ton immersed tube, Jinan No. 1 set sail from the dry dock under precise timing. At 1:00 a.m., the vessel reached the designated lowering position in the middle of the channel. Crews guided the immersed tube into position using a sophisticated network of cables. Slowly and carefully, the massive structure descended to the trench. Engineers then connected the new tube section to the previous one using pole rods. To maintain installation accuracy, divers transmitted real-time underwater footage, allowing the team above to monitor every step. After an hour of meticulous fine-tuning, engineers reduced the deviation at the joint to just 0.8 millimeters, thinner than a human eyelash. This achievement broke the world record for underwater immersed tube alignment. Dutch supervisor Janssen, witnessing the event, documented the moment in his logbook and described it as the Apollo moment of engineering. This comparison reflected the sheer scale, ambition, and precision of the operation, an undertaking that stood alongside humanity's greatest engineering triumphs. With the Shenzhen-Zhongshan Bridge now fully operational, a new megastructure graces the Pearl River estuary. When the first vehicle headlights cut through the darkness of the undersea tunnel, the moment symbolized far more than the rebirth of a critical transportation artery. It marked a monumental dialogue between humanity and the ocean, a testament to what engineers can accomplish when they combine vision with execution. The entire project represents a fusion of strength, intelligence, and innovation. From intelligent factories that enabled the production of massive, corrosion-resistant immersed tubes, to precision machinery that leveled and prepared the seabed with almost surgical accuracy, every phase of the project embodied technical mastery. The use of self-compacting concrete, poured by intelligent robots and monitored by thousands of sensors, compressed traditionally labor-intensive processes into efficient, repeatable workflows. Engineers ensured that every detail, down to the molecular-level anti-corrosion coatings and the placement of sacrificial anodes, guaranteed the tunnel's durability for at least a century. The Shenzhen-Zhongshan link now stands as a testament to what is possible when human ingenuity challenges nature's limits. Engineers turned obstacles into opportunities, transforming rough seabeds, massive weights, and unforgiving marine conditions into a triumph of modern infrastructure. The project not only connects cities and economies, but also inspires future generations to dream beyond the horizon. The Infrastructure Revolution. Chief Engineer Song Xinyu reflected on the monumental achievement of the Shenzhen-Zhongshan Bridge by stating that the team spent 16 years transforming a bold concept on paper into an everyday reality for millions. He emphasized that while the Hong Kong-Zhuhai-Macau Bridge serves as a maritime connection uniting Guangdong, Hong Kong, and Macau, the Shenzhen-Zhongshan Bridge acts as the pivotal gateway to unlocking the economic potential of the Pearl River estuary's Golden Inner Bay. Together, these massive infrastructure undertakings have dramatically accelerated the economic integration of the Greater Bay Area, fostering a unified region poised for long-term prosperity. Song's insight underscores the broader impact of Chinese engineering, creating not just structures, but also opportunities that catalyze regional development. Chinese engineers have long moved beyond theoretical designs to create what were once unimaginable feats: bridges that leap across turbulent seas, tunnels that burrow beneath mountains, and expressways that spiral above clouds. These projects form a vast transportation network, enabling seamless movement across vast distances and connecting cities, countrysides, and economies. In doing so, Chinese infrastructure has become a global symbol of scale, complexity, and speed, showcasing a national capability that draws attention from every corner of the world. From the majestic Yaxi Expressway weaving through mountainous terrain to the record-breaking bridges and tunnels piercing the peaks of Sichuan and Chongqing, engineers have turned formidable natural obstacles into lifelines of commerce and connection. By overcoming 7 world records during construction, they have not only improved livelihoods, but also revitalized rural regions, paving the way for economic equity and mobility. Infrastructure as a national brand. The Hong Kong-Zhuhai-Macau Bridge stands as the most technically challenging and structurally complex bridge ever built in the history of road construction. It shattered multiple world records and established core technologies now recognized as national assets. These achievements are not merely feats of engineering, but symbols of self-reliance and innovation, driven by independently developed Chinese intellectual property. When the Shenzhen-Zhongshan Bridge and the Huangmao Cross-Sea Bridge officially opened in 2024, the Greater Bay Area reached a new milestone: the realization of a 1-hour living circle. This concept, where travel times between major cities are reduced to under an hour, has reshaped the region's social and economic dynamics. Roads and bridges have collapsed the barriers of time and space, fostering coordinated growth and shared prosperity across formerly disconnected areas. The expansion of China's railway network reflects a similar transformation. By investing in independent research and pioneering construction techniques, China has reshaped everyday life for its people. With the world's most extensive high-speed rail and highway systems now in place, traversing thousands of miles in a single day is no longer a privilege but a daily norm. These systems represent more than just speed. They symbolize the nation's capacity to tackle world-class engineering challenges and deliver real-world solutions that uplift communities and drive economic development. This relentless drive has earned China the nickname Infrastructure Maniac, a title that celebrates not only technical mastery, but also the scale and ambition with which the country approaches each project. China's influence extends well beyond its borders. Through large-scale international projects, Chinese engineers have exported their expertise to nations seeking modernization and economic expansion. Each project abroad carries with it the same commitment to quality, innovation, and efficiency that defines domestic infrastructure development. Whether constructing roads in Africa, railways in Southeast Asia, or ports in the Middle East, Chinese engineers have become catalysts for growth in developing countries. Behind this global leadership lies a powerful combination of technological advancement and national will. Since the founding of the People's Republic, China has risen from devastation to prosperity through decades of perseverance and innovation. Generations of engineers have toiled, struggled, and achieved, building the foundation of a thriving and connected China. However, China does not view this as a final destination. The infrastructure maniac's journey continues, with new frontiers ahead. China intends to assist more developing nations on their paths to modernization, creating new avenues for economic opportunity and better living conditions across the globe. Each bridge, tunnel, and railway built under this initiative connects not only geographic locations, but also unites diverse populations, bringing the future within reach for millions. These projects bridge the past and the present, the domestic and the international, weaving together a vision of progress rooted in shared prosperity and mutual growth. China's infrastructure achievements have not only altered its landscape, but have also become a testament to the country's strength, determination, and spirit. Each project represents more than concrete and steel. It embodies a story of transformation, ambition, and relentless pursuit of progress. As the infrastructure maniac continues to shape the world, one can only imagine what new milestones lie ahead. What engineering miracles will Chinese infrastructure achieve in the next decade? Share your thoughts in the comments, and remember to subscribe and stay informed. Until next time, see you in the next video.